It began, as all great revolutions in thought often do, with something small, ordinary, and easily missed. A quiet afternoon, a wandering mind, and a single apple falling from a tree. The year was 1766, and Isaac Newton was not yet the legend carved into textbooks. He was a man in solitude, a thinker sent home from Cambridge as the plague spread across England. The world outside his window was chaos, but inside his mind, something extraordinary was taking shape. He sat beneath an apple tree, not as a poet seeking metaphor, but as a scientist haunted by a question. Why did the apple fall straight down? Why not sideways, or upward, or in some unpredictable curve? The fruit had not been pushed. There was no visible tether drawing it to the ground. Yet it moved with purpose, as if guided by an invisible hand. That invisible hand, he would later call gravity. Newton's law of universal gravitation was both elegant and astonishingly bold. Every object in the universe, he declared, pulls every other object with a force. The strength of this pull depends on two things: the masses of the objects and the distance between them. Two stones attract each other, two stars attract each other, and so does an apple and the earth beneath it. The same principle that brings the apple to the ground keeps the moon in its orbit, binding the heavens and the earth under one law. For the first time, the cosmos appeared unified, as if the same invisible threads stretched from orchard to orbit. But Newton's triumph carried a quiet discomfort. He could describe the behavior of gravity, but not its cause. What was this invisible connection that reached across empty space? How could the earth exert a pull on the apple without touching it? Even Newton himself found this notion troubling. He called it action at a distance, a phrase that carried both wonder and unease. In his letters, Newton admitted that the mechanism by which gravity acted was something he could not yet imagine. He wrote that it was inconceivable that inanimate matter could act upon another matter through a vacuum, without something else mediating the effect. But lacking a better answer, he left the question hanging in the dark between the stars. And so, for more than 2 centuries, scientists lived comfortably in Newton's universe, a vast mechanical stage where every planet, comet, and falling stone obeyed precise mathematical rules. The equations worked so perfectly that few dared question the invisible strings that made them possible. The universe was a clock, and gravity was one of its gears. Yet deep in the foundations of that clockwork world, something remained incomplete. Newton's law described how masses attract, but not why. What carried that influence across the void? Was space itself merely an empty arena, or could it be part of the story? The question lingered like static beneath the harmony of the celestial symphony. By the 19th century, the problem grew more pressing. The discovery of electromagnetic fields by Faraday and Maxwell hinted that invisible forces could indeed ripple through empty space. Perhaps gravity too had its own kind of field, an unseen sea connecting all things. But the mathematics of Newton's gravity could not capture such a phenomenon. It assumed an instantaneous pull, that the sun, if it were suddenly to vanish, would cause the earth to drift away at once. Yet even common sense rebelled against that idea. Nothing, not even light, moves infinitely fast. So how could gravity act without delay? The seeds of doubt took root in a young patent clerk working in Bern, Switzerland, in the early years of the 20th century. His name was Albert Einstein, and he carried Newton's question forward with the stubborn curiosity of someone unwilling to accept mystery for its own sake. If Newton's laws were the melody of motion, Einstein wanted to find the rhythm beneath it, the deeper geometry that might explain why anything moves the way it does. Einstein began by questioning the nature of motion itself. His theory of special relativity, completed in 1905, revealed that time and space are not separate entities, but two faces of a single continuum, spacetime. In that realization, the stage of the universe came alive. No longer a static backdrop, it became a flexible entity that could stretch, contract, and perhaps even bend. When he turned this insight toward gravity, the picture transformed completely. What if, Einstein wondered, gravity was not a force pulling through space, but a feature of space itself? What if the apple fell not because the Earth was tugging on it, but because the space around the Earth was curved, and the apple simply followed the curve? It took Einstein 10 years to find the mathematics that could express this vision. In 1915, he unveiled his general theory of relativity. Its message was simple yet profound. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. In one elegant stroke, the invisible force of Newton became the geometry of Einstein. The falling apple was not being pulled at all. It was moving naturally along a straight path in a curved world. That realization forever changed the way we see the universe. Gravity was no longer a mysterious string between masses. It was the shape of reality itself, warped by the presence of energy. The stage was no longer separate from the actors. It was part of the performance. Yet even as Einstein's equations redefined the cosmos, a new question emerged. If mass and energy curve spacetime, what gives spacetime its ability to bend at all? What is this fabric made of? And could it too be something deeper than it appears? The mystery of the falling apple had only just begun. The story of gravity did not end beneath that apple tree, nor did it end with the equations that once bound planets to invisible strings. As centuries unfolded, the idea of motion and force itself began to evolve. To the scientists of the 18th and 19th centuries, Newton's equations were scripture. They predicted the paths of comets, guided cannon fire, and mapped the tides. Yet there remained a whisper of uncertainty, a sense that gravity's explanation was not a conclusion, but a bridge to something deeper. Every test confirmed Newton's law, but as measurements became more precise, tiny cracks appeared in the perfect clockwork. The orbit of Mercury, for instance, refused to obey the law exactly. Its path around the Sun drifted slightly with each revolution, an unexplained precession that defied the predictions of classical mechanics. Astronomers speculated there might be another planet hidden near the Sun, a secret world named Vulcan, whose gravity could explain the deviation. But no planet was ever found. The universe, it seemed, was sending a quiet message. Something fundamental was missing. Into this uncertainty stepped Albert Einstein. By 1905, he had already changed the world once, showing that light's speed is the ultimate limit and that energy and mass are equivalent. Two forms of the same entity, united by the equation that would become as iconic as Newton's apple. But Einstein sensed that the true revolution still waited in the shadows. He knew that the notion of gravity as an invisible force was incomplete, perhaps even an illusion born of the way we perceive motion. He began with a simple thought. Imagine a man falling freely in space. Inside his small cabin, everything floats beside him. He cannot tell whether he is drifting in empty space or falling toward a planet. This simple idea, that gravity and acceleration are locally indistinguishable, became the cornerstone of what Einstein called the equivalence principle. From that seed, a grander vision began to unfold. If gravity and acceleration were the same, then perhaps the experience of being pulled downward was not a force at all, but the geometry of the world curving beneath our feet. The Earth bends the structure of space-time around it, and the apple, the man, and even light itself follow the curves of that geometry. In that sense, gravity is not something acting upon an object. It is the path that object naturally takes through a curved landscape of reality. Einstein spent 10 years chasing the mathematics that could make this picture precise. He wrestled with tensor calculus, explored the geometry of curved surfaces, and nearly gave up more than once. But persistence, the quiet companion of genius, carried him through. In November of 1915, he presented the equations of general relativity to the Prussian Academy of Sciences. At first glance, the equations appeared cryptic, a dense network of symbols and indices. But beneath their complexity lay a breathtaking simplicity. Spacetime tells matter how to move, and matter tells spacetime how to curve. There was no longer any need for an invisible force to stretch across the cosmos. Gravity emerged naturally from the shape of the universe itself. To understand this, one must picture space and time not as separate dimensions, but as a single fabric, four-dimensional, seamless, and dynamic. Massive objects like stars or planets warp this fabric, creating depressions and curves. When another object, such as a planet or an apple, moves nearby, it simply follows the straightest possible line through this curved geometry. To us, it looks like attraction, but in truth, it is motion through a distorted stage. The beauty of Einstein's theory is that it turned intuition inside out. The apple is not pulled to the earth. It is simply falling along the shortest path through space-time. The Earth does not hold the Moon in orbit with a tugging force. The Moon moves freely, following the curvature the Earth's mass creates. Even light, though massless, bends around stars because the space it travels through is no longer flat. When the theory was first proposed, many doubted it. It was too strange, too unlike the neat mechanical universe people had come to trust. But in 1919, during a total solar eclipse, the English astronomer Arthur Eddington measured the apparent position of stars near the sun's edge. Their light bent exactly as Einstein had predicted. The discovery made global headlines. Light all askew in the heavens read the newspapers, and Einstein became a household name. The universe had curved before humanity's eyes. Yet, behind the triumph, a deeper mystery remained. Einstein's equations explained how space-time curves, but not what it truly is. The theory was silent about the substance of this fabric. Was space-time merely mathematical abstraction, or did it have a physical essence? Could it vibrate, ripple, or even tear? These questions would echo through the next century, inspiring physicists to seek the quantum threads that might weave reality itself. The falling apple, once the symbol of a simple pull toward the Earth, had now become a window into the structure of existence. Its descent revealed not an invisible force, but a stage that bends under the presence of energy. Still, the question persisted. What grants space-time this astonishing flexibility? How does the geometry of reality respond to mass and motion? Somewhere, deep within those equations, the answer seemed to shimmer. As if gravity were not a thing that acts, but a story that unfolds between energy and the shape of the world. Einstein's insight did not just rewrite physics, it rewrote philosophy. No longer was space the emptiness between things. It was an entity, an actor in the cosmic drama, alive with structure and tension. The universe was not a machine of separate parts. It was a single, self-interacting whole. Still, as complete as Einstein's picture seemed, it opened more questions than it closed. If space could bend, could it also twist, stretch, and ripple? Could the geometry of space-time carry waves the way a pond carries ripples from a thrown stone? And if so, what happens at the smallest scales, where the smoothness of space-time might dissolve into something even more fundamental? In the shadow of those questions lay the next frontier, a deeper search for the source of curvature itself. The realization that space and time could bend was so radical that even Einstein himself felt awe at its implications. He would later write that it was as though he had glimpsed the mind of God, not in a theological sense, but in the pure harmony of mathematical law and physical truth. Yet for all its beauty, the theory demanded evidence, and evidence soon came, not just from starlight bending around the sun, but from the slow dance of planets and the steady ticking of time itself. The planet Mercury, whose orbit had long puzzled astronomers, moved exactly as Einstein's equations predicted. The mysterious precession that Newton's laws could not explain was not caused by an unseen planet, but by the subtle curvature of space-time near the sun's immense gravity. Even the flow of time itself was revealed to be relative. Near massive objects, clocks tick more slowly, as if the very rhythm of existence softens under the weight of gravity. The apple that fell in Newton's orchard did not simply obey an invisible pull. It was following the natural slope of space-time, the same geometry that governs the path of planets, the bending of light, and the slowing of time. Gravity, in Einstein's universe, was no longer a force, but a conversation between matter and geometry, between energy and the shape of reality. As physicists tested these ideas, they found that every observation strengthened the new picture. The bending of light, the expansion of the universe, the orbit of binary stars, all echoed the same truth. Space-time was not an abstract grid laid over reality. It was reality, molded by whatever occupied it. Yet, as often happens in science, each answer gave birth to deeper mysteries. If mass and energy curve space-time, then what exactly counts as energy? Einstein's equations did not privilege matter. Anything that carries energy, light, radiation, even pressure, has the power to warp geometry. The universe, it seemed, was a tapestry constantly shaped by everything within it. Consider light itself. Though massless, it still carries momentum, and momentum is a form of energy. When a ray of light grazes a star, it does not travel in a perfectly straight line, but follows the star's curvature in space-time. To an observer, it appears as though the light has been deflected by gravity. In truth, it has simply followed the shortest possible route through a curved geometry. The path of least resistance is no longer a straight line, but a graceful arc through the landscape of space-time. Einstein once described his discovery as replacing Newton's mysterious pull with a simple statement. There is no gravitational force, only the geometry of motion. That geometry is dynamic, elastic, and alive. It stretches under the weight of suns and collapses into depths around black holes. The universe, once imagined as a static machine, is now seen as a living fabric that flexes and flows. But what is that fabric made of? This question, so simple in wording, and yet so profound in consequence, has haunted physicists ever since. Einstein could describe how curvature behaves, but not what gives space-time its form. In his mathematics, space-time was continuous, infinitely divisible, smooth, and unbroken. But nature, as later discoveries in quantum physics would reveal, does not always play smoothly. Beneath the surface, the universe is granular, composed of discrete quanta of energy. So how can something continuous, like the curvature of space-time, emerge from something discrete, like the quantum world? This paradox sits at the heart of modern physics. Gravity, as Einstein described it, is a geometric phenomenon, elegant and deterministic. Quantum mechanics, born only a decade after his theory of relativity, is probabilistic and chaotic, governed by uncertainty. Between them lies an unresolved tension, a rift that no theory has yet fully bridged. Yet, despite this divide, the two realms must meet. For there are places in the cosmos, the hearts of black holes, the first moments after the Big Bang, where gravity and quantum mechanics collide. There, space-time curvature becomes infinite, and Einstein's equations can no longer describe reality. The geometry itself breaks down, and the notion of distance or time ceases to make sense. To understand gravity fully, we must uncover the source of its curvature, not just in stars and galaxies, but in the microscopic structure of existence. What gives space-time its elasticity? What medium allows it to warp, twist, and ripple? Could it be woven from something even more fundamental? A network of quantum events, or patterns of information that shape geometry from below? These questions mark the horizon that Einstein could see, but never cross. In his later years, he searched for a unified field theory, a single framework that would bind gravity and electromagnetism, matter and geometry into one coherent picture. He never found it, yet his pursuit continues in the work of those who followed. Physicists seeking quantum gravity, string theory, and the idea that space-time itself may be emergent, not fundamental. Still, before we reach that frontier, we must understand what truly causes curvature, not metaphorically, but physically. Einstein showed that energy and momentum are the architects of geometry, encoded in what he called the stress-energy tensor. Every form of energy, from the glow of a photon to the pressure within a star, contributes to the bending of space-time. In this sense, gravity is the shape that energy carves into reality. The more energy present, the deeper the curve. When a massive star collapses into a black hole, the curvature becomes so extreme that even light cannot escape. When the universe expands under the influence of dark energy, it is the geometry itself stretching outward. Everywhere we look, curvature is the dialogue between energy and the cosmos. The falling apple, then, was never just a story of attraction. It was a story about the shape of existence, how energy molds the stage upon which all things move. From Newton's orchard to Einstein's equations, humanity's understanding of gravity had evolved from a pull through emptiness to the realization that emptiness itself is something capable of bending. And yet, even this revelation is not the final word. For if space-time can curve, ripple, and twist, what lies beneath that fabric? What gives it the ability to respond to energy? What is the true substance of the universe's geometry? 2 centuries after Newton's wonder beneath the apple tree, Einstein's insight opened a new kind of mystery. Not about the apple's fall, but about the nature of the space it falls through. The path forward would lead deeper still, into the structure of energy and the hidden architecture of space-time itself. The age of forces was ending. The age of geometry was about to begin. Einstein once said that imagination is more important than knowledge, for knowledge defines all that we know and understand, but imagination embraces the entire world. When he conceived of space-time, he did not imagine a force tugging across emptiness. He imagined the emptiness itself coming alive. Space was no longer a silent void, and time no longer a universal metronome ticking the same everywhere. Together they formed a living fabric, one that could stretch, curve, and ripple under the influence of energy. To reach that idea, Einstein had to take a leap beyond what could be seen. He began with an experience of falling. A person in free fall feels no weight, no sense of gravity pressing down. In that instant, gravity disappears. This simple realization revealed something profound. Gravity and acceleration are indistinguishable. What we feel as gravity is the resistance of the ground preventing us from following our natural path through space-time. Remove the ground, and we drift freely along that curvature, unaware that anything is pulling at all. The equivalence principle, as it came to be known, became Einstein's compass. It suggested that gravity is not a force acting at a distance, but a manifestation of geometry. Objects in free fall are not being drawn by invisible lines. They are following the straightest possible paths through a curved 4-dimensional landscape. These paths are called geodesics, and they are the natural routes through space-time. Much like great circles on the surface of a sphere are the shortest routes between 2 points. To understand how this geometry behaves, one must first abandon the comfortable picture of 3-dimensional space and a separate flow of time. In Newton's world, the two were independent. Space was the stage, time the clock. Einstein shattered that division. In relativity, space and time intertwine into a single continuum. A change in motion through space affects motion through time, and vice versa. The faster one moves through space, the slower one moves through time. Every object, every beam of light, every particle follows its own rhythm through this 4-dimensional symphony. Now imagine this space-time as flexible, not rigid. When mass or energy occupies a region, it distorts the geometry around it. Picture a vast cosmic fabric. Place a heavy sphere upon it, and the fabric dips. Nearby objects roll toward that dip, not because they are being pulled, but because the surface they move along is curved. The apple near the Earth near the Sun, and the Sun within the galaxy all follow this same rule. But this image, as helpful as it is, must be treated carefully. The fabric is not a physical sheet stretched across a higher dimension. It is the very metric by which distance and duration are measured. When space-time curves, the meaning of straightness and simultaneity changes. Clocks tick differently, rulers stretch or contract, and light follows bent paths not because it is forced to, but because straight lines themselves have changed shape. Einstein's general theory of relativity encodes this relationship in a single, elegant equation. On one side is geometry, represented by the Einstein tensor, a mathematical description of curvature. On the other side lies the stress-energy tensor, describing the distribution of energy and momentum. The equation reads, in symbolic form, that geometry equals energy content multiplied by a constant of proportionality. It is the most compact statement of the universe's architecture ever written. Matter tells space-time how to curve, and curved space-time tells matter how to move. From this simple statement, every gravitational phenomenon arises. The fall of an apple, the orbit of planets, the bending of starlight, the slow ticking of clocks near massive bodies, and even the expansion of the entire universe, all emerge from the same geometric principle. It was not a new force, but a new way of seeing. The cosmos was no longer a mechanical system of pushes and pulls, but a continuous dance of shape and motion. When Einstein finally published his equations in 1915, the reaction among scientists was divided. Some were captivated by their elegance, others skeptical of their strangeness. But the true power of a theory lies in its predictions, and general relativity predicted phenomena no other theory could explain. One of the first was the correction to Mercury's orbit, which matched observation perfectly. Another was the deflection of starlight by gravity, which would soon be confirmed during the solar eclipse of 1919. In that moment, as the stars near the sun's edge shifted ever so slightly in the photographs, humanity saw the universe curve. The confirmation electrified the world. Newspapers hailed Einstein as the new Newton, the discoverer of cosmic truth. But what made his theory more than just a refinement of Newton's was not accuracy, it was vision. He had revealed that space and time are not containers for reality. They are reality, their curvature defining everything that happens within them. Yet Einstein himself remained humble. He often said that the most incomprehensible thing about the universe is that it is comprehensible. He had transformed the mysterious pull of gravity into the shape of existence itself. But he never lost the sense of wonder that began with that simple act of imagining what it would be like to fall. The leap he made was not just scientific but philosophical. If space-time can bend, then the geometry of the universe is not imposed from outside, but arises from within. There is no stage separate from the performance, no clock external to the ticking of reality. Everything interacts with everything else, and the whole evolves according to its internal harmony. This vision would redefine not only physics, but our understanding of existence. The universe, in Einstein's eyes, was a self-consistent geometric organism, and though his equations described how space-time curves, they also implied a deeper mystery, that curvature itself must arise from something. Geometry cannot exist without energy, and energy cannot exist without geometry. They are two aspects of one cosmic dialogue. The leap from Newton's invisible force to Einstein's dynamic space-time was complete. But as with all great revolutions, it was not the end of the story. It was the beginning of a larger one. For once we accept that mass and energy curve space-time, we must ask what exactly determines the shape of that curvature, how energy sculpts geometry, and whether curvature itself might someday reveal what space-time is truly made of. The next step would take humanity even deeper into that question, into the very source of curvature itself. Einstein's discovery was more than an explanation of gravity. It was an invitation to rethink the very scaffolding of the cosmos. He had written down equations that spoke a language older than words. a language of geometry and symmetry, in which the presence of energy told the universe how to shape itself. But what does that truly mean? What does it mean for energy, something intangible and invisible, to bend the architecture of reality itself? To grasp this, one must understand what Einstein placed on the right side of his equations, the entity known as the stress-energy tensor. Despite its intimidating name, it is simply a way of describing how energy and momentum are distributed and how they flow through space-time. It tells not only how much energy exists at a point, but also in what direction that energy is moving, how it exerts pressure, and how it interacts with neighboring regions of the universe. Every object, from a drifting atom to a blazing star, contributes to this grand ledger of energy and momentum. Even light, though massless, has energy, and that energy influences geometry. The stress-energy tensor is the handwriting of reality itself, describing the pulse of every field, the shimmer of every photon, and the pressure of every gas and plasma. When it changes, the shape of space-time responds. Einstein realized that gravity is not a force transmitted through emptiness, but the expression of this interaction between energy and geometry. The Earth bends space-time not because it chooses to, but because its energy, its mass, and even its internal pressure demand that space-time curve in a certain way. The curvature is not an effect layered on top of reality, it is reality. To picture this, imagine a sheet of fabric representing space-time. A heavy sphere placed on it creates a depression, a visual metaphor often used to explain gravity. But this is only an analogy. In truth, space-time is four-dimensional, and the curvature happens in ways that cannot be fully imagined in our three-dimensional minds. It is not just the bending of space, but the warping of time itself. Clocks near a massive object tick more slowly, and distances subtly change their meaning. Einstein's equations describe this interplay with astonishing precision. The geometry of space-time, captured in the curvature tensor, adjusts itself perfectly to match the energy described by the stress-energy tensor. When energy increases, curvature deepens. When energy flows, space-time flexes and ripples. It is as if the universe itself breathes, its fabric rising and falling with the tides of energy that move within it. This relationship is not one way. Matter shapes space-time, but space-time also guides matter. A planet orbits a star not because it is being pulled, but because the geometry around the star tells it what the straightest path looks like. In curved space-time, straight paths appear as orbits, ellipses, or spirals. To move without force, to simply follow the shape of the world, is what we perceive as falling. This insight rewrote the human understanding of motion. For millennia, scientists had thought of motion as requiring cause, a push, a pull, a force acting from one body to another. Einstein showed that motion could be geometry. When a spacecraft drifts through interplanetary space, it is not coasting through emptiness. It is tracing a line through a curved and evolving space-time, a geometry sculpted by suns, planets, and the faint cosmic background of energy that fills the void. Even regions once thought empty are never truly so. Space-time itself contains energy, stored in its curvature, its expansion, and its fluctuations. The equations of relativity treat this energy as real, meaning that even the vacuum contributes to gravity. The more we explore, the more we realize there is no such thing as nothingness. Every region of the cosmos hums with the potential to bend. In the early 20th century, this concept seemed almost mystical, yet experiment after experiment confirmed it. Light passing near massive objects followed bent paths. Clocks placed in airplanes and on mountaintops ticked at slightly different rates. The precise orbits of satellites could not be explained without accounting for the curvature of space-time. These effects, once thought minuscule, became essential in the age of technology. Global positioning systems, which rely on the synchronization of atomic clocks, must include corrections from Einstein's theory to remain accurate. Without general relativity, the navigation signals guiding aircraft and ships would drift by kilometers each day. The equations also revealed something even more profound. Gravity travels at the speed of light. In Newton's world, a change in mass would instantly alter its gravitational influence everywhere. But Einstein's universe had no place for instantaneous action. If the sun were to vanish, the Earth would continue its orbit for 8 minutes. The time it takes light to travel from the sun to the Earth, before feeling any change in spacetime's shape. Gravity, like light, moves as a wave through the cosmic fabric. These waves, known today as gravitational waves, are ripples in spacetime caused by accelerating masses. When two black holes spiral together, they send out bursts of curvature that travel across the universe, stretching and squeezing the fabric of reality as they go. For a century, these waves were only a prediction, but in 2015, the Laser Interferometer Gravitational Wave Observatory detected them directly for the first time, proving beyond doubt that space-time can vibrate. The cosmos is not still, it resonates. Einstein's leap had revealed a living universe, one in which geometry itself is a participant. Space and time are not containers. They are elastic and reactive, molded by energy, reshaping everything that moves through them. Yet, even in the midst of such clarity, the question remained: if curvature arises from energy, what gives energy its power to bend? The deeper one goes, the more it seems that the distinction between matter, energy, and space begins to blur. Perhaps they are not separate entities, but facets of the same underlying essence. The field equations do not explain what space-time is made of, only how it behaves. They show the choreography, not the dancers. To uncover what lies beneath the geometry itself, physics would need to venture into the quantum world, a realm where certainty dissolves and where even space and time might lose their meaning. But before that leap, one truth remains luminous. Gravity is not a force pulling things together. It is the very shape of togetherness. It is the way energy tells reality what form to take. Every fall, every orbit, every ripple in the night sky is a trace of that conversation between mass, energy, and the fabric of space-time. The truth of space-time curvature began to unfold not in equations alone, but in the sky itself. Each new observation became a window into the bending of reality. For centuries, the heavens had seemed a realm of perfect geometry, distant and untouched, the silent clockwork of Newton's laws. But Einstein's leap transformed that clockwork into something living and fluid. What once appeared as eternal balance was revealed to be a dynamic ocean of curved geometry, constantly shaped by the energy within it. The first hints came from light, that most fundamental messenger of the cosmos. Light, in Newton's world, traveled straight through an absolute space, unbent and unerring. But in Einstein's world, light has no choice but to follow the geometry it moves through. When starlight grazes the sun on its way to the Earth, it curves ever so slightly, its path redirected by the sun's warped space-time. It does not bend because something pulls on it. It bends because straightness itself has changed meaning. This bending of light, called gravitational lensing, became one of the first great confirmations of Einstein's theory. During the total solar eclipse of 1919, Arthur Eddington's expedition to the island of Principe measured the positions of stars near the darkened sun. The light had shifted precisely as general relativity predicted. The universe had revealed its curvature, not through metaphor, but through measurement. For the first time in history, humanity saw the cosmos bend under its own weight. Since that day, gravitational lensing has become a tool for exploring the invisible. Galaxies far beyond our own act as lenses, their mass-bending light from even more distant sources. Through this distortion, astronomers can map dark matter, that unseen substance that outweighs ordinary matter by a factor of 5. The bending of light reveals not only the visible universe, but also the shadows of the unseen. Space itself becomes a lens, a cosmic mirror of its own curvature. Time, too, is caught in the same geometry. Near massive objects, time flows more slowly. A clock on the surface of the Earth ticks at a slightly different rate from one in orbit. This is not a trick of perception, but a fundamental property of curved space-time. In the geometry of the universe, the flow of time depends on position, motion, and gravitational potential. Time itself stretches and compresses as if woven into the folds of the cosmic fabric. This phenomenon, known as gravitational time dilation, has been tested with exquisite precision. In laboratories, atomic clocks separated by only a few meters show measurable differences in their ticking rates when placed at different heights. In orbit, satellites circling the Earth must correct their onboard clocks for both special and general relativistic effects. Without those corrections, the global positioning system would lose accuracy within hours. Every time a phone guides a traveler through a city, it relies on Einstein's curved spacetime to know where it is. To live on the surface of the Earth is to live inside a gravitational well, a gentle depression in the geometry of spacetime. We do not notice it because everything around us is equally curved: our rulers, our clocks, even the rhythms of our hearts. But if we could step outside this curvature, if we could hover far from any mass, we would see time speeding up and space flattening. In the far reaches between galaxies, space-time stretches so evenly that its geometry approaches perfection. Not truly flat, but close enough that light travels almost straight for billions of years. And yet, even the vast emptiness between galaxies is not static. Space-time ripples. It shivers with gravitational waves, disturbances caused by massive bodies in motion. When two neutron stars spiral toward each other, or when black holes collide, the very shape of space-time quakes. These waves travel at the speed of light, carrying information about cataclysmic events across the universe. They do not pass through space. They are space changing its form. For a century, these waves were a whisper in Einstein's equations, undetectable by any instrument. But on a September morning in the year 2015, two laser detectors, thousands of kilometers apart, caught the faintest tremor ever measured. A pair of black holes, more than 1 billion light-years away, had merged, sending ripples through space-time that stretched and squeezed the Earth by less than the width of a proton. Humanity had heard the sound of gravity itself, a deep cosmic note resonating through the geometry of reality. With that discovery, Einstein's vision became complete. Space and time were not abstractions, not backdrops, not vessels to contain events. They were the very medium of existence, responsive and alive. Gravity was no longer a mysterious force pulling masses together, but the rhythm of the universe itself, the curvature that energy inscribes into being. And yet, as this picture grew clearer, a deeper question began to emerge, one that would haunt physicists through the century that followed. If energy bends space-time, what gives space-time the capacity to bend? What is this fabric that stretches and ripples like something tangible, yet has no substance we can touch? Einstein's equations describe its behavior, but not its essence. They tell us how curvature arises, but not why space-time possesses elasticity at all. The fabric metaphor helps the imagination, but it does not reveal the mechanism. What property of reality allows geometry itself to respond to energy as if it were material? Some physicists began to suspect that space-time might not be fundamental. Perhaps it emerges from something deeper, a hidden network of quantum interactions, or the structure of information woven at the smallest scales. Others believed space-time to be the most primal entity, the stage that creates all else, from fields to particles. Between these views lies the most profound mystery in physics, whether the universe is made of geometry or whether geometry itself is made of something else. As telescopes grew sharper and detectors more precise, they began to expose subtle discrepancies. hints that Einstein's equations, though nearly perfect, might not be the full story. At the extremes of black holes and the birth of the cosmos, where curvature becomes infinite, the theory falters. The geometry collapses into singularities where time loses meaning and the fabric of space seems to tear. It is here, at the limits of curvature, that the next great question emerges. What lies beneath the geometry itself? If energy shapes space, and space in turn shapes motion, then the source of curvature must lie deeper still. Somewhere in that hidden layer may be the key to uniting Einstein's smooth continuum with the quantum world's restless granularity. The leap from Newton to Einstein had transformed the universe from a machine into a living fabric. But the next leap would demand an even greater imagination, one that could see not only the curvature of space-time, but the mysterious energy that creates that curvature in the first place. The journey into that mystery begins with a question both elegant and profound. What, precisely, is the source of curvature? The moment Einstein's equations appeared on paper, they whispered a truth as deep as any ever written. On one side stood geometry, the curvature of space-time, the shape of reality itself. On the other side stood energy and momentum, the contents of the universe, everything that moves, radiates, and exists. Between them stretched a perfect balance. Geometry equals energy content. The heart of that balance is something known as the stress-energy tensor, a mathematical object so rich that it holds within it the story of how every bit of energy, every flicker of light, and every ounce of matter bends the universe around it. It is not just mass that creates gravity, as Newton once thought. It is energy in all its forms: mass, motion, pressure, radiation, even the tension within fields. Every movement of energy leaves its signature in the geometry of space-time, shaping it like wind shaping the surface of an ocean. The stress-energy tensor may seem abstract, but its meaning is profoundly physical. It tells how much energy resides in each region of space-time, and how that energy flows. It encodes the momentum of particles, the pressure within gases, the energy density of starlight, and the very fabric of the vacuum itself. When one writes the equation that links geometry and energy, it is not merely a formula. It is a dialogue written in the language of the universe, where energy speaks and space-time listens. This relationship gives rise to one of the most beautiful truths in all of physics. The curvature of space-time is the response of the universe to the presence and movement of energy. If mass and energy were to vanish, space-time would flatten into perfect stillness, no curvature, no gravity, no motion. But the universe is never empty. From the burning of stars to the faint hum of cosmic radiation, energy is everywhere, and with it, curvature. Imagine a massive star floating in the quiet depths of space. Its energy warps the geometry around it, creating a well in space-time. Nearby, a smaller object, perhaps a planet, moves along the curves of that well. It is not being pulled by a force, but simply following the straightest path through curved space-time. The deeper the well, the stronger the apparent attraction. This is why a black hole, a collapsed star with infinite density, bends space-time so severely that nothing, not even light, can escape its grip. Yet even this image of space-time bending like a flexible fabric is only an analogy. What truly curves is not a surface, but the very metric that defines distances and durations. When space-time curves, the meaning of near and far, before and after, changes. Time slows near a massive object because the geometry of time itself has stretched. Light bends, not because it is deflected, but because straightness has been redefined. Every motion in the cosmos, from the fall of an apple to the orbit of galaxies, is a trace of this geometric truth. The stress-energy tensor reveals something even more surprising. Not only matter and mass, but pure energy itself can curve space-time. Light, though massless, carries momentum. When two beams of light cross, they exert gravitational influence on each other, however faint. Pressure, too, has weight. Inside the core of a star, where the heat of nuclear fusion creates immense pressure, that pressure itself adds to the star's gravitational pull. Even the energy contained in electromagnetic or quantum fields contributes to curvature. The universe bends not only under matter, but under motion, tension, and radiation. Einstein's vision united all these phenomena under one principle. The geometry of the universe is determined by the distribution and flow of energy. Every spark, every wave, every pulse contributes to the shape of existence. This insight means that the universe is not merely a stage for events, it is sculpted by them. The motion of galaxies, the collapse of stars, and even the faint background glow left from the Big Bang all participate in the shaping of spacetime's geometry. The most direct evidence of this interplay comes from how light travels through the cosmos. When a ray of light passes near a massive body, such as a star or galaxy, it does not move in a straight line through empty space. Instead, it follows the curvature that energy has inscribed. The path of the light tells us how spacetime itself is shaped. This is how astronomers map the invisible, by tracing the distortions in light that reveal where mass and energy lie hidden. At the heart of every galaxy lies a supermassive black hole, a concentration of energy so extreme that it creates a region where the curvature of spacetime becomes infinite. There, the geometry folds in upon itself, forming a boundary from which nothing can return. Yet even at such extremes, Einstein's equations hold true, describing the contours of this invisible abyss with remarkable accuracy. The black hole does not pull matter in. Spacetime simply bends inward so sharply that all paths lead down. This bending of spacetime can be visualized as the universe's response to energy's presence. Just as ripples spread across a pond when a stone is dropped, changes in energy and momentum send ripples through spacetime, gravitational waves. These waves propagate outward, carrying information about the events that created them. They are the heartbeat of the cosmos, faint yet eternal, whispering the story of every violent merger, every collapsing star, every trembling horizon. But energy does more than shape the universe, it sustains it. Even regions that appear empty are filled with fields and fluctuations. Quantum theory tells us that space is never truly still. Particles and antiparticles flicker in and out of existence in a restless dance, borrowing energy from the void and giving it back in a fraction of a second. This vacuum energy, though invisible, has real gravitational effects. It may be the reason the universe's expansion is accelerating, driven by a mysterious phenomenon we now call dark energy. If even the vacuum contributes to curvature, then Einstein's equation speaks of a universe where everything matters. No bit of energy, no flicker of motion is without consequence. Every photon, every vibration, every quantum fluctuation contributes, however slightly, to the shaping of the whole. Reality is a web of cause and curvature, energy and geometry woven together so tightly that they cannot be separated. And yet, within this perfect harmony lies a profound mystery. If energy curves spacetime, what gives energy itself the ability to do so? What property of energy commands geometry to respond? Einstein's equation states the relationship but does not explain its origin. The stress-energy tensor is the map, not the terrain. Somewhere beneath it lies the mechanism, the reason the universe responds to energy with curvature rather than indifference. Physicists have spent a century searching for that deeper truth. Some suspect that gravity emerges from quantum interactions, that spacetime is not continuous but composed of countless microscopic connections, and curvature is simply the large-scale behavior of those quantum links. Others believe that the answer lies in information itself, that the geometry of spacetime may be the shape taken by the flow of quantum information between particles. Whatever the answer, one thing is certain. The curvature of spacetime is not an illusion, but neither is it the end of the story. It is the visible face of an invisible structure, the surface of something deeper that connects energy, motion, and existence in ways we are only beginning to glimpse. For now, the equations remain our guide, and they tell us that everything, everywhere, contributes to the bending of the universe. The stars above, the air we breathe, even the warmth of our own bodies participate in the shaping of reality. To exist is to curve space-time. And so, the question that began with a falling apple and grew into Einstein's geometry has reached a new depth. Gravity is not the pull of distant bodies, but the conversation between energy and the universe's shape. Yet still, one question remains. If curvature is caused by energy, what gives space-time its power to bend at all? What makes this fabric capable of responding? The next step in our journey will explore that question, to see curvature in action, to watch light and time themselves bend and ripple under the influence of energy, and to understand how we can measure the invisible geometry that defines our reality. The effects of curvature are written across the cosmos like hidden signatures waiting to be discovered. For those who know where to look, the sky becomes a mirror of space-time's shape. Every distortion of light, every shift in time, every trembling of the cosmic web tells the same story. That energy and momentum do not simply inhabit the universe, they define it. Consider first the simplest and most elegant of these manifestations, the bending of light. When light from a distant star passes near a massive body, such as a galaxy or a black hole, its path curves. To an observer, the starlight appears displaced, as if it came from a different position in the sky. Sometimes the light from a single galaxy splits into multiple images, or stretches into rings and arcs, a phenomenon called gravitational lensing. These are not tricks of optics, but direct expressions of space-time curvature. The geometry itself redirects light, turning the universe into its own telescope. Gravitational lensing has become one of the most powerful tools in modern astronomy. By studying how light from distant galaxies is distorted, scientists can map the invisible distribution of mass, not only the visible stars and gas, but also dark matter, that unseen component making up most of the universe's mass. The bending of light reveals where gravity hides. Every arc of distorted starlight is a photograph of space-time's curvature, a visual imprint of energy's unseen hand. Even time, that quiet and relentless current, is drawn into this geometry. Near a massive object, time flows more slowly. A clock placed near the surface of a planet ticks at a gentler rhythm than one floating high above it. This effect, called gravitational time dilation, is not mere theory. It has been measured countless times with extraordinary precision. In 1976, a small atomic clock was flown aboard a rocket to a height of 10,000 kilometers. When compared with identical clocks left on the ground, the airborne clock had ticked slightly faster by a few billionths of a second, just as Einstein's equations predicted. Time itself had stretched and compressed according to space-time's curvature. Today, this same principle keeps the modern world synchronized. The satellites that orbit the Earth as part of the global positioning system rely on clocks so precise that even a tiny relativistic discrepancy would cause navigational errors of kilometers each day. Engineers must account for both the slowing of time due to the Earth's gravity and the speeding of time due to the satellite's motion. Without these corrections, the entire network of navigation, communication, and trade would unravel. In every digital map, in every signal guiding a ship or a plane, Einstein's curvature silently operates. The most dramatic evidence of space-time's curvature, however, comes from the motion of light near black holes. When light grazes the event horizon, it is caught in a gravitational grip so intense that it bends back upon itself. Some light escapes after orbiting the black hole several times, producing a glowing halo called the photon ring. Others fall inward, vanishing from the universe. In 2019, the Event Horizon Telescope captured the first direct image of such a ring surrounding the supermassive black hole at the center of galaxy M87. What we saw was not the black hole itself, for no light can emerge from within, but the warped geometry around it, space-time twisted into a luminous whirlpool. The image, blurred yet unmistakable, was humanity's first glimpse of gravity, sculpting light into form. But curvature is not confined to the colossal. It unfolds at every scale, even within our own bodies. Every particle of matter exerts its own tiny distortion on space-time. Though infinitesimal, these curvatures collectively shape the world we experience. The air, the oceans, the mountains, all contribute, their mass and energy gently bending the local geometry. We live within this curvature every moment, our hearts ticking in rhythm with the warped fabric of time. The most astonishing discovery of the 20th century, however, was that space-time can ripple. When massive objects accelerate, for instance, when two neutron stars spiral together, they disturb the geometry around them. These disturbances propagate outward at the speed of light, stretching and squeezing space-time as they travel. Gravitational waves are the purest expression of the relationship between energy and curvature, for they carry no matter, only the motion of space-time itself. For decades, these waves remained undetected, their effects far too faint to measure. But technology caught up with Einstein's vision. In the year 2015, a pair of black holes collided more than 1 billion light-years away, releasing a burst of gravitational energy that momentarily outshone all the stars in the observable universe. When that wave reached the Earth, it passed through the detectors of the Laser, Interferometer, Gravitational Wave Observatory. The instrument's laser beams stretched and compressed by less than a fraction of a proton's width, yet that whisper was enough. The universe had spoken through its curvature. Since then, dozens of such events have been recorded, each one a story told in the language of geometry: collisions of black holes, mergers of neutron stars, cosmic symphonies played on space-time's invisible strings. These waves confirm what Einstein had always suspected. Gravity is not static, but alive, capable of motion and resonance. Through these observations, the once abstract mathematics of general relativity has become the most precise description of the universe ever written. Every experiment, every satellite, every telescope confirms it. From the fall of an apple to the trembling of distant galaxies, all motion obeys the same geometry. The equations hold across scales vast and minute, elegant in their simplicity, relentless in their truth. Yet the more they succeed, the more they reveal their incompleteness. For while Einstein's theory describes how energy curves space-time, it does not tell us why space-time responds to energy at all. It shows the pattern, not the mechanism. When we observe light bending, time slowing, or waves rippling, we are witnessing effects without yet understanding the cause beneath them. Physicists now suspect that space-time may not be the fundamental layer of reality, but a vast emergent phenomenon, a tapestry woven from quantum threads too small to see. In this view, curvature might be the large-scale expression of interactions among countless microscopic entities, like the smooth surface of water hiding the frantic motion of molecules beneath. If that is true, then the stress-energy tensor is not the ultimate source of curvature, but merely its visible reflection, a shadow cast by a deeper architecture. The next frontier of science will be to uncover that hidden structure, to peer beneath the smooth geometry of Einstein's universe and discover the quantum skeleton that supports it. But before we dive into that hidden realm, one more truth must be grasped. Curvature is not confined to stars and black holes. It is everywhere, even in the emptiness between galaxies. The vacuum itself, far from being nothing, contains energy, and that energy bends space-time in ways both subtle and immense. The story of curvature, then, is not only about how energy shapes space, but how space itself possesses energy. And that realization will take us to the next chapter, where even nothingness becomes a source of gravity. Even emptiness, it turns out, is not truly empty. The deeper we peer into the fabric of space-time, the more we find it alive with energy. Einstein's equations do not merely respond to matter, they respond to everything that carries energy or momentum. This includes not only the visible stars and galaxies, not only the heat of their burning cores, but also the invisible sea that fills what we once thought of as void. When physicists first examined the equations closely, they noticed something profound. Energy does not have to be concentrated in solid matter to produce curvature. Radiation, pressure, and even the energy of empty space itself can bend the geometry of the universe. Every region of space-time carries within it an energy density, and that density acts as a source of gravity. Light, for instance, has no rest mass, yet because it carries energy and momentum, it warps the geometry around it. When two beams of light cross, each subtly alters the other's path. The effect is unimaginably small, but it exists, written in the mathematics of relativity. This means that even in a universe filled only with light, gravity would still exist, the geometry would still curve, and the waves of radiation would still follow those curves. Pressure, too, contributes to curvature. In the heart of a star, where nuclear fusion pushes outward with unimaginable force, that pressure itself has weight. It adds to the gravitational field, making the star's pull slightly stronger than it would be from its mass alone. Pressure and energy density are inseparable. They are two faces of the same entity, both woven into the stress-energy tensor that defines how space-time bends. This realization changed how scientists viewed the cosmos. It meant that the architecture of the universe is not shaped only by things, but by the relationships and tensions between things. Wherever energy flows, wherever light travels, wherever pressure builds, the geometry of reality adjusts. The universe is constantly reshaping itself in response to its own contents, an eternal dialogue between energy and form. Even the concept of emptiness dissolved under this understanding. What appears to us as empty space, the dark void between stars and galaxies, is filled with fields that vibrate even in their lowest possible state. Quantum physics revealed that these fields never rest. They fluctuate with energy, creating virtual particles that appear and vanish in unimaginably short timescales. This restless activity gives rise to what we call vacuum energy, the baseline hum of existence that pervades all of space-time. Though the individual fluctuations cancel on average, their cumulative effect is enormous. The energy of the vacuum, tiny at human scales, becomes vast when considered across the whole cosmos. According to Einstein's equations, this vacuum energy should curve space-time just like ordinary matter does. And indeed, it does, on a scale so large that its influence shapes the destiny of the universe itself. In the early years of the 20th century, Einstein added a term to his field equations known as the cosmological constant, representing a uniform energy density filling space. At the time, he introduced it only to maintain a static universe, as astronomers then believed the cosmos was neither expanding nor contracting. Later, when Edwin Hubble discovered that galaxies were receding from one another, Einstein abandoned the constant, calling it his greatest blunder. But the blunder was not a mistake. It was a prophecy. Decades later, observations of distant supernovae revealed that the expansion of the universe is not slowing down, as gravity would suggest. It is accelerating, driven by some mysterious form of energy permeating space itself, what we now call dark energy. In the language of Einstein's equations, this is precisely what the cosmological constant describes. Vacuum energy, the energy of nothingness, is pushing the universe apart. This discovery transformed our understanding of cosmic curvature. For centuries, we imagined gravity as the agent that pulls things together. But the universe has shown us another side of gravity, one that pushes outward. When energy density takes the form of vacuum energy, it acts not as attraction, but as repulsion. It causes space-time to stretch, expanding faster and faster, carrying galaxies away from each other like leaves on a rising tide. The same equations that describe the fall of an apple now describe the expansion of the cosmos. The curvature that draws matter together in one place causes space itself to expand in another. The sign of curvature, whether it bends inward or outward, depends on the nature of the energy that fills it. Mass and ordinary energy curve space-time inward, creating wells and orbits. Vacuum energy curves it outward, inflating it across unimaginable distances. We live within this tension. The universe expands because the vacuum has energy, yet that same energy could one day determine its fate. If dark energy remains constant, galaxies will drift forever, stars will fade, and space will stretch into darkness. If it changes, the expansion could slow, halt, or even reverse, leading to a cosmic collapse. In every possible future, curvature remains the language through which energy speaks to existence. Even now, the geometry of spacetime carries the imprint of all that has ever existed. The cosmic microwave background, the faint afterglow of the Big Bang, shows minute fluctuations in temperature, evidence of small variations in density and curvature present when the universe was young. Those ripples grew over billions of years into galaxies, clusters, and the vast filaments of matter we see today. From the quantum tremors of early energy fields to the curvature of spacetime that guides their evolution, the universe's structure is a direct consequence of energy-shaping geometry. When we look into the night sky, we are not merely seeing stars scattered in space. We are looking at the folds and curves of spacetime itself, stretched and molded by energy over cosmic history. Every photon that reaches our eyes has traveled along a path dictated by curvature, weaving through the invisible geometry sculpted by all that exists. Einstein's insight, once confined to equations, has become the foundation of modern cosmology. The entire history of the universe, its birth, its expansion, and its possible end, is encoded in the dialogue between energy and curvature. Gravity is no longer simply a story about falling. It is the grand narrative of existence itself, where even nothingness participates in shaping the whole. Yet for all this elegance, one mystery still remains unsolved. If vacuum energy curves spacetime, what gives spacetime the property of responding? What makes it elastic? What allows the geometry of the universe to expand, ripple, and bend as though it were a material, though no substance can be found within it? To answer that question, physics must journey beyond Einstein, into the quantum realm, where spacetime itself may not be smooth, where curvature may not be continuous, and where the fabric of the cosmos may be woven from threads of probability and uncertainty. There, at the smallest scales imaginable, gravity may not be geometry at all, but the emergent echo of something deeper. The source of curvature has led us to the brink of that hidden frontier. Beyond it lies the question that will define the next century of physics. What gives rise to the fabric of space-time itself? For centuries, gravity was invisible. It could be felt, it could be calculated, but it could never be seen. Newton described it as a pull across space, and Einstein reimagined it as the bending of space and time themselves. Yet for most of human history, these ideas lived only in mathematics and imagination. Then, slowly, through the steady precision of experiment, gravity began to reveal its face. The curves of space-time, once only a theory, became visible in the bending of light, the ticking of clocks, and the rhythm of the stars. The first vision of curvature came from the heavens. When the light of distant stars passed near the sun, it shifted slightly, as though the stars themselves had moved. This was the test that changed everything. During the total solar eclipse of 1919, the English astronomer Arthur Eddington and his team journeyed to the island of Principe to photograph the stars near the sun's darkened edge. When the images were compared, the starlight had bent by exactly the amount Einstein had predicted. It was as though space itself had curved to cradle the path of light. The newspapers of the world erupted with awe. Revolution in science, they declared. Newtonian ideas overthrown. For the first time, humanity had measured the shape of reality. The invisible had become visible. Gravity was not an unseen force stretching across emptiness. It was geometry itself, revealed by the bending of light. Over the decades that followed, new eyes opened to the sky, and with them came new confirmations of Einstein's vision. Astronomers discovered that entire galaxies could act as lenses, bending and magnifying the light from even more distant galaxies behind them. Sometimes the curvature was so strong that a single background galaxy appeared as multiple images, or even as a complete circle of light called an Einstein ring, born from the perfect alignment of matter and light. Through these cosmic lenses, scientists could now see what had once been hidden: the invisible scaffolding of the universe. The pattern of curved light revealed that most of the cosmos is made not of stars, but of dark matter, unseen mass that exerts gravity but emits no light. The bending of light around clusters of galaxies traced its presence like fingerprints in glass. Each distortion told of gravity's silent hand shaping the vast architecture of the universe. But curvature is not only written in the paths of starlight, it is written in the flow of time itself. Near massive bodies, time slows. The stronger the gravitational field, the slower the rhythm of existence. This phenomenon, called gravitational time dilation, is not poetic metaphor. It is measurable, and it has been measured countless times with extraordinary precision. In the 1960s, physicists Robert Pound and Glenn Rebka sent gamma rays up a 75-foot tower at Harvard University. The rays gained a tiny bit of energy as they fell, exactly as Einstein's theory predicted. Time was running slightly faster at the top of the tower than at the bottom. The difference was microscopic, but real. A proof that gravity alters time even over small heights. Today, our most advanced atomic clocks can detect differences in time between 2 points only a few centimeters apart in height. Raise one clock onto a shelf, and it ticks faster than the one left on the floor. The effect is so precise that it must be accounted for in technologies we use every day. The global positioning system, orbiting high above the Earth, depends on dozens of satellites, each carrying atomic clocks. These clocks experience both special relativity, because of their speed, and general relativity, because they are farther from the Earth's gravitational field. Without adjusting for these effects, GPS would accumulate errors of kilometers within hours. The system works only because Einstein's equations are woven into its design. Every navigation signal that reaches a phone or a ship is a whisper from curved space-time. Gravity's reach extends not only through time and light, but through motion itself. When a spacecraft travels near a planet, it can use that planet's curvature to gain speed, a maneuver called a gravitational assist. The craft does not burn extra fuel or receive a push. It simply follows the geometry of space-time, borrowing a sliver of momentum from the planet's motion. The Voyager probes, launched in the 1970s, used these assists to escape the solar system entirely, carrying humanity's presence into interstellar space. Each of these examples, from the fall of light to the ticking of clocks, reveals a small piece of the same truth. Space-time is not a static backdrop, but a living structure, one that stretches, bends, and responds to energy. Yet even these subtle curvatures are only the gentlest whispers of a far greater power, the ability of space-time not just to curve, but to move. In the year 1916, Einstein predicted that when massive objects accelerate, they should send ripples through space-time, gravitational waves. These waves, he believed, would carry energy outward at the speed of light, distorting space and time as they passed. But the waves were so faint that Einstein doubted they would ever be detected. For almost a century, they remained hidden, beyond the reach of every instrument. Then, in September of 2015, the Earth shuddered by a distance smaller than a proton. Two black holes, more than 1 billion light-years away, had merged. The collision sent a ripple through space-time, stretching and squeezing the planet ever so slightly. The Laser Interferometer Gravitational Wave Observatory, called LIGO, caught the signal, a faint oscillation that lasted only a fraction of a second. But within that moment was the sound of gravity itself. When the signal was converted to audio frequencies, it became a chirp, a quick rising tone that marked the final spiral of two black holes colliding. For the first time, humanity had not only seen the universe bend, but heard it move. Einstein's geometry had spoken in vibration. Since that first detection, dozens of gravitational waves have been recorded. Each one tells a story of cataclysmic events, the merging of black holes, the collision of neutron stars, the violent heartbeat of space-time. These signals confirm beyond doubt that gravity is not a force at all, but a dynamic feature of the universe, capable of carrying information, energy, and motion across billions of light-years. The detection of gravitational waves also marked a profound shift. For the first time, humanity became aware not just of objects in space, but of the motion of space itself. The universe is not silent. It hums with the faint music of curvature, the vibrations of creation still echoing from distant corners of time. Einstein's theory, born from imagination and mathematics, now guides the most advanced experiments ever built. We measure time with clocks that feel gravity's pull, navigate the planet with satellites that orbit through curved spacetime, and listen to the faint songs of the cosmos as spacetime ripples through us. The invisible has become measurable. Gravity has become light and sound, movement and rhythm. Every experiment confirms that we live not within emptiness, but within a vast flexible geometry that shapes and responds to everything we do. The apple falling, the Earth orbiting, the galaxy spinning, and the universe expanding are all expressions of the same conversation between energy and curvature. Yet behind this harmony, a deeper question remains. If space-time can bend and move, what gives it the capacity to do so? What grants the universe its elasticity? The next chapter will turn inward, beyond observation and measurement, to explore the very nature of the fabric itself, the mysterious entity that underlies all motion, all geometry, and all existence. The story of curvature is not over. The cosmos has shown us its shape, but not yet its substance. To find that, we must look beyond the equations, into the essence of space-time itself. The evidence for curvature did not stop with the eclipse or the first photographs of bending light. As instruments grew more precise, scientists began to watch the very rhythm of the cosmos shift under gravity's invisible hand. Time itself became a measurable proof of Einstein's idea. In every experiment that followed, time behaved as the geometry demanded. The Hafele-Keating experiment in 1971 sent atomic clocks aboard commercial airplanes circling the world in opposite directions. When the clocks returned, they disagreed with identical clocks left on the ground. The results matched exactly what Einstein's theory predicted. The motion of the airplanes and the gravity of the Earth had both altered the flow of time. Hours may seem absolute to human senses, but the universe keeps no universal rhythm. Each observer lives within their own tempo, sculpted by their motion and their position in space-time. The confirmation of this truth reshaped technology. Without general relativity, modern civilization would lose its bearings within moments. The global positioning system depends on the precise ticking of satellites in orbit. Each clock runs faster than one on the surface because gravity's grip weakens with distance. At the same time, each runs slower because of its high speed relative to the Earth below. Engineers must correct for both effects. The satellites transmit signals that carry these corrections, so that when a phone on Earth receives them, the device can calculate its position within meters. Every location, every direction, every flight path and map projection owes its accuracy to Einstein's geometry. Even in laboratories, gravitational time dilation has become an everyday fact. Atomic clocks, now measure time so finely that moving one clock up a single meter in height changes its ticking rate enough to detect. This means that time flows differently for your feet and your head. In the mathematics of relativity, this is not a curiosity, but a necessity. Time slows where gravity is stronger because the path through space-time is deeper. Each tick of a clock marks the unfolding of a curve. The bending of light and the slowing of time were once abstract ideas. They have now become engineering principles. The world runs on relativity, whether we notice it or not. Yet the most powerful expression of curvature still remained hidden, waiting to be heard rather than seen. In 1916, Einstein wrote that when massive bodies move and accelerate, they should send ripples through the very geometry of existence. These ripples, called gravitational waves, would spread through the universe at the speed of light. They would not travel through space. They would be space changing its shape. For decades, this remained speculation. The distortions were too faint for any instrument to detect. Then, in the late 20th century, an indirect clue appeared. Two astronomers, Russell Hulse and Joseph Taylor, discovered a pair of neutron stars orbiting one another. Over years of observation, they saw the stars spiraling slowly inward. Energy was leaking from the system at exactly the rate Einstein's theory predicted for gravitational wave emission. It was not a direct detection, but it was a sign that space-time could indeed carry energy as a wave. Still, the final proof required an instrument sensitive enough to measure a change smaller than an atom across kilometers of distance. That proof came in 2015, when two black holes merged in a distant galaxy. The collision released a wave that traveled for more than 1 billion years before brushing across the Earth. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, recorded a signal lasting less than a second. The mirrors of its detectors, separated by thousands of meters, shifted by a fraction of a proton's width. When scientists converted the data to sound, it produced a faint chirp. That tiny sound carried the story of two black holes colliding, releasing more energy in a moment than all the stars of the visible universe combined. It was the first time in history that humanity had heard the voice of space-time. In that instant, Einstein's theory transformed from mathematics into music. The universe proved that its geometry is not fixed but dynamic. It trembles, sings, and carries information through its own fabric. Each gravitational wave detection since then has added another verse to that cosmic song. Some waves come from colliding black holes, others from merging neutron stars. Each one tells of energy turning into motion, and motion turning into curvature. When the collision of two neutron stars was detected in 2017, telescopes across the world turned to the same patch of sky. For the first time, light and gravity were observed together from a single event. The flash of gamma rays and the ripple of space-time arrived almost simultaneously, confirming that gravitational waves travel at the same speed as light. The unity of space-time was complete. Gravitational waves are now a new kind of astronomy. They let us observe the universe through its own heartbeat rather than through light. Light can be blocked or absorbed, but gravity passes through everything. Through it, we can listen to events hidden from view, to black holes merging in darkness, to the echoes of creation itself. These discoveries mark the transition of relativity from theory to experience. Einstein's geometry has become the foundation upon which we measure the world. Every second of every day, technology depends on it, from communication satellites to navigation, from astrophysics to the operation of power grids that synchronize by atomic time. The once abstract curvature of space-time has become a practical reality, woven into the fabric of modern life. Still, even now, we do not know what that fabric truly is. We can describe how it bends, we can measure how it ripples, but we do not yet know what gives it the ability to move. If space-time were simply a mathematical abstraction, it could not flex or vibrate. There must be something physical behind its geometry, something deeper than the equations. This question leads directly to the next great step in understanding gravity. What is space-time made of? What gives it its resilience, its capacity to warp and to carry waves? The experiments that revealed curvature have answered the question of how gravity acts, but not why. The next chapter will look beneath the equations, into the heart of the fabric itself, to uncover what reality is truly made of. To see curvature in action is to witness the universe express its own structure. Every experiment, every observation, reveals a piece of the same truth. Space-time is alive with motion. It bends, stretches, and ripples, carrying the memory of every event that has ever taken place. In the centuries before Einstein, the universe was imagined as a stage, an empty arena where matter moved and light traveled. Today, that image has dissolved. The stage itself moves with the players. Space is not a void but a participant, a fabric that changes shape as energy flows through it. Every atom, every star, every photon alters its texture. We do not live in space, we live within a living geometry. Modern astronomy has turned that geometry into a laboratory. When light from a distant galaxy bends around another on its way to us, it paints a map of curvature. By studying these distortions, astronomers reconstruct the hidden structure of the universe. The most massive galaxies sit at the intersections of invisible filaments of dark matter, forming a cosmic web that stretches across billions of light years. This web is not simply a distribution of matter, it is the shape of space-time itself, frozen in light. At smaller scales, the same principles govern the technology that defines our daily lives. The time signals that guide aircraft and synchronize financial systems all rely on the precision of relativity. Even our understanding of the Earth itself depends on these corrections. Satellite data must account for the curvature of space-time to map the planet's shape and gravity field accurately. Without Einstein's geometry, our measurements would drift, our navigation would fail, and the modern world would lose its balance. What began with an apple has grown into the architecture of civilization. Gravity is no longer only the force that pulls, it is the geometry that connects. Every fall, every orbit, every pulse of time reveals that energy and space-time are inseparable. The universe is not held together by invisible strings, but by the continuous conversation between mass, motion, and geometry. The more precisely we observe, the more profoundly this unity reveals itself. In regions of extreme gravity, such as near black holes, the bending of space-time becomes so strong that even light cannot escape. There, time slows almost to a stop. The boundary between where light can leave and where it cannot is called the event horizon. At that edge, space-time curves back upon itself. To an outside observer, an object falling into a black hole appears to freeze at the horizon, its image fading slowly as the light that carries its story grows redder and weaker. Inside, the geometry becomes so warped that our equations fail to describe it. It is there, in the hearts of black holes, that the limits of Einstein's theory appear most clearly. The mathematics predicts infinite curvature, a point where the laws of physics break down. Such singularities are places where geometry ceases to be defined. They are the cracks in the smooth fabric of space-time, hints that something deeper must exist beneath it. Yet even as black holes conceal the limits of our understanding, they also reveal the beauty of Einstein's vision. When the Event Horizon Telescope captured the first image of a black hole in the galaxy M87, what we saw was not the object itself, but its shadow against a glowing halo of light. That light was bent by gravity as it circled the black hole multiple times before escaping. The image was a photograph of space-time curvature, a portrait of geometry made visible. Every observation since then has confirmed the same truth. The bending of light, the slowing of time, and the rippling of space-time are not separate effects, but expressions of the same fundamental reality. Curvature is the language in which the universe speaks. Matter, energy, and motion are its vocabulary. Even in the vastness of intergalactic space, where the stars grow sparse and the silence deepens, curvature remains. The cosmic microwave background, the faint afterglow of the Big Bang, carries small fluctuations in temperature and density. Those fluctuations mark places where curvature was slightly greater or smaller in the early universe. Over billions of years, these tiny differences grew into galaxies and clusters. The entire structure of the cosmos arose from the geometry of space-time, responding to the distribution of energy. The more we measure, the more we see that curvature is everywhere. It is not confined to distant phenomena or extreme events. It shapes the path of every photon and the rhythm of every clock. It determines how the universe expands and how galaxies cluster. It is not a side effect of gravity, it is gravity, the very shape of reality responding to energy. But behind all these manifestations lies a deeper mystery. Space-time behaves as though it were an elastic fabric, capable of stretching and bending. Yet no one knows what grants it that flexibility, what gives geometry its strength, its ability to move. The equations describe how curvature behaves but remain silent on what it is made of. If space can bend, if time can slow, if the universe can ripple like a vast ocean, then the fabric of space-time must have properties beyond mere abstraction. It must be something real, something that can store energy, carry motion, and sustain waves. What is that something? The search for an answer leads to the frontier where Einstein's smooth geometry meets the restless quantum world. At that scale, the continuous fabric may dissolve into discrete fragments, a granular texture where the distinction between space and energy begins to blur. The experiments that revealed curvature have opened the door to this deeper question. We can now see and hear the geometry of space-time, but we still do not understand its substance. The next step is to ask what the universe's fabric truly is and whether it is fundamental or emergent. Gravity has revealed itself not as a force, but as a shape. The next challenge is to uncover what creates that shape. The path forward leads into the very structure of reality, into the equations that describe how geometry and energy intertwine, and into the mystery of what gives rise to the fabric itself. The universe has shown us that space and time are alive. The next chapter will ask what that life is made of. When Einstein wrote his equations, he gave the universe a new kind of substance. Space and time were no longer mere settings for events. They were dynamic participants in the cosmic drama, bending, stretching, and rippling in response to energy and momentum. Yet even as the theory triumphed, it left a haunting question unanswered. What is space-time itself made of? In Newton's world, space was the stage. In Einstein's, it became the actor. But an actor must have form. It must have properties that allow it to move, to carry waves, to bend and return to shape. Space-time behaves as if it were elastic, yet it is not made of anything we can touch or see. It has no atoms, no substance in the ordinary sense. The very idea of a fabric implies a weave, yet this weave has no threads. To understand how something can be both structure and emptiness, physicists turn to the heart of Einstein's field equations. On one side of the equation lies geometry, represented by a quantity called g mu nu. This term describes the curvature of space-time, how lines converge or diverge, how volumes expand or contract, and how time itself flows. On the other side lies T mu nu, the stress-energy tensor, describing the distribution of matter, radiation, and energy. Between them sits a constant that links the two, 8 pi times the gravitational constant. The equation can be spoken simply. Geometry equals energy content. The shape of space-time is determined by what it contains. Every bit of energy changes the curvature, and every curve guides the motion of energy. It is a dialogue between the form of reality and its contents, a conversation so perfect that neither side can exist without the other. This equation is not just mathematics. It is the architecture of existence. It means that the universe is self-consistent, that its shape and its matter are forever intertwined. The Earth orbits the Sun not because it is pulled, but because it follows the natural path within the curved geometry created by the Sun's energy. The same equation explains the motion of galaxies, the behavior of black holes, and even the expansion of the cosmos itself. Yet the equation also hints at mystery. If energy defines curvature, then something must give spacetime the ability to curve. There must be a physical quality that allows geometry to respond to energy, just as metal bends under stress or water ripples under wind. The mathematics works, but it does not say what this property is. Physicists sometimes compare spacetime to an ocean, smooth on the surface but concealing depths beyond imagination. The waves on this ocean are gravitational waves, the ripples of geometry we have now learned to hear. But what lies beneath the surface? What is the medium that carries these ripples? When light travels through glass or air, we know it is moving through a medium, its speed depending on the properties of that medium. When gravitational waves travel, they move through spacetime itself. But what gives spacetime the ability to transmit them? This question leads to the very limits of general relativity. The theory describes how geometry behaves, but not what geometry is. Some scientists imagine spacetime as a kind of field, a continuous entity that fills the universe. Others think it may be emergent, a large-scale effect of countless microscopic interactions, much like temperature emerges from the random motion of molecules. In this view, the smoothness of spacetime would be an illusion, the visible face of a deeper quantum structure. Evidence for this may already be hidden in the mathematics. At the Planck scale, where distances become unimaginably small, the concepts of length and time lose their ordinary meaning. Quantum fluctuations become so intense that spacetime itself begins to tremble. The fabric may not be continuous at all, but composed of discrete units, tiny quanta of geometry. The search for these quanta has inspired entire fields of research, from string theory to loop quantum gravity. Each offers a different vision of what the fabric might be. String theory proposes that every particle and every force is a vibration of an unimaginably small string of energy, and that spacetime itself arises from the interactions of these strings. Loop quantum gravity, on the other hand, imagines spacetime as woven from loops of quantized area and volume, forming a network like an invisible lattice. Both ideas share one crucial insight. The curvature we see, the bending that governs the motion of planets and the structure of galaxies, may not be fundamental. It may be the large-scale behavior of something deeper, something that connects quantum mechanics and geometry. Einstein's equations, though monumental, may describe only the surface of this deeper reality. They tell us how curvature responds to energy, but not what endows the universe with that ability. To find that, physicists must look where gravity becomes strongest and where quantum effects become unavoidable, such as near black holes or in the first moments after the Big Bang. At those extremes, general relativity and quantum theory begin to clash. Relativity treats spacetime as smooth and continuous, while quantum mechanics insists that everything comes in discrete packets. Somewhere between them must lie the truth, a description of reality that unites the smooth and the granular, the geometric and the probabilistic. If we could see the universe at that smallest scale, perhaps we would not find a continuous fabric at all. Perhaps we would find a vast network of relationships where space, time, and energy are not separate things, but different expressions of the same underlying pattern. The curvature we observe may then be nothing more than the way that pattern organizes itself, the macroscopic shape of a deeper order. The implications reach beyond physics. If spacetime is not a fixed arena, but an emergent phenomenon, then reality itself is a process, not a thing. The universe is not built from matter sitting in space. It is built from interactions that are space. Geometry becomes the stage and the story, the rule and the result. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. The equation that connects geometry and energy embodies that wonder. It shows that everything from falling apples to spinning galaxies obeys the same simple principle. Yet it also reveals that we have only glimpsed the surface. Beneath the elegance of the equation lies an unfinished question, waiting for the next leap of understanding. The fabric of reality is not merely curved, it is alive. It listens to energy, it carries waves, it changes with time. It is the medium through which the universe becomes aware of itself. And still, the question echoes. What is the fabric made of? What gives rise to its structure and strength? To approach that mystery, we must leave the smooth surface of relativity and descend into the quantum world, where the geometry of space-time begins to break apart, where uncertainty replaces continuity, and where gravity itself may emerge from the restless motion of the smallest possible things. The idea that space-time is both geometry and energy is one of the most beautiful and unsettling in all of science. It says that reality is self-shaping, that energy does not exist inside space, but creates it. The universe, in this view, is not a stage filled with actors, but an improvisation where the stage itself responds to every movement. The field equations of Einstein are deceptively simple when written, but they contain the architecture of all existence. They state that the geometry of spacetime, symbolized by g mu nu, equals 8 pi times the gravitational constant multiplied by the stress-energy tensor, T mu nu. Geometry equals energy content. That is the essence of general relativity. Every part of this equation carries meaning. The term g mu nu represents how space-time bends, how time slows, and how distance warps. The term T mu nu describes how energy, pressure, and momentum are distributed. The gravitational constant connects them, translating the strength of energy into the degree of curvature. Together, they describe how the universe shapes itself. When we look at the world through this lens, we see that geometry and physics are not separate subjects. They are the same phenomenon seen from two directions. Matter tells space-time how to curve, and curved space-time tells matter how to move. Energy is not placed into space, it defines space. Every point in the universe is determined by the flow of energy through it. The equation does not only apply to planets and stars. It governs the smallest particles and the largest galaxies alike. It explains why light bends near the sun, why black holes trap everything within them, and why the universe expands. It is the same law, scaled across all of creation. Yet within that perfection lies a puzzle. The equation works only because space-time behaves as though it were flexible. It stretches, contracts, and carries waves as though it possessed tension and elasticity. But how can emptiness have such properties? What gives it the ability to behave like a material when by definition it is not made of matter? Physicists wrestled with this paradox for decades. Some argued that space-time must be a kind of field, a continuous entity that fills the universe and interacts with matter. Others thought of it as a purely mathematical abstraction, a way to describe relationships between events without implying a physical medium. But every experiment kept pointing to the same truth. Space-time behaves like something real. When gravitational waves pass through the Earth, they stretch and compress space itself. When light curves around a star, it is following the geometry of the universe. When time slows near a planet, it is because the fabric of space-time is deformed. These are not metaphors. They are measurable. The geometry has physical effects, and those effects have consequences for everything that exists. Einstein himself sometimes described space-time as a kind of elastic continuum, though he resisted imagining it as a substance. He understood that the idea of a medium could reintroduce the concept of absolute space that his own theory had destroyed. Yet the equations behaved as if space-time had structure. The curvature responded to energy the way a stretched membrane responds to pressure. If we push this idea further, we arrive at a remarkable conclusion. The universe could be thought of as a single object, with space-time as its body and energy as its pulse. The galaxies, stars, and planets are not separate pieces moving through an external space. They are excitations within the fabric itself, the patterns of its curvature. This picture is both humbling and profound. It means that every movement, every force, every beam of light is part of the same continuous entity. The motion of your body, the orbit of the moon, and the dance of distant galaxies are all ripples in the same fabric. The universe is not a collection of things in space. It is space, shaped by energy. The field equations also reveal why gravity is universal. Unlike the other forces which act through specific fields or particles, gravity arises from the geometry of space-time itself. Everything that has energy must move within that geometry, and thus everything experiences gravity. No particle can escape it because it is not a separate force. It is the shape of motion itself. When we walk, when we drop an object, or when the Earth circles the Sun, we are not being pulled by invisible strings. We are following natural paths through curved space-time, paths called geodesics. These are the straightest possible lines within a curved geometry. An apple falls because the geometry around the Earth guides it downward. A planet orbits because its path curves within the geometry of the Sun's mass. This understanding transforms our notion of cause. The apple does not fall because the Earth acts upon it. It falls because space-time itself is shaped in such a way that falling is the straightest path available. Gravity is no longer a force transmitted across distance, but a condition of existence. Einstein's insight also explains why gravity cannot be shielded. You can block light with a wall, deflect magnetism with a material, but you cannot block curvature. To exist within space-time is to participate in its geometry. There is no outside of it. Wherever energy is, curvature follows. At the same time, this interconnectedness raises new questions. If curvature depends on energy, and energy is distributed through the stress-energy tensor, then what happens when we reach the smallest scales, where quantum mechanics dominates? Energy there does not behave smoothly. It fluctuates wildly, appearing and disappearing in bursts. If space-time reacts to energy, then these fluctuations should make it tremble. Physicists call this the problem of quantum gravity. At large scales, the geometry is smooth and predictable, following Einstein's equations precisely. At small scales, the geometry should boil and foam, breaking apart into quantum uncertainty. Somewhere between these two extremes lies the truth, a unified description of gravity that includes both Einstein's continuum and quantum discreteness. The search for this unity has led to the exploration of theories like string theory, which proposes that everything is made of tiny vibrating loops of energy, and loop quantum gravity, which treats space as composed of discrete chunks of area and volume. Both are attempts to explain what gives space-time its elasticity, what underlies the curvature we observe. No matter which theory proves correct, they all share a single idea. Space-time's ability to curve must come from something deeper than geometry itself. Curvature is not the cause, but the effect. Beneath it lies the true fabric of the universe, a network of interactions so fundamental that space, time, and matter emerge from it as byproducts. If that is true, then Einstein's equations are like the surface of a sea. They describe the waves, not the water. The next great discovery in physics will come when we understand what the water is. And so, once again, we arrive at a threshold. We can measure curvature, we can hear its waves, we can even see its shadow in black holes. But we do not yet know what gives the universe its flexibility, what makes geometry respond to energy as though it were alive. To answer that, we must look deeper still into the quantum nature of space-time, where smooth curves dissolve into restless motion, and where the very concept of space begins to lose its meaning. The deeper one looks into space-time, the more it begins to resemble a living network rather than an empty stage. Einstein's equations tell us how curvature behaves, but they do not tell us what creates the fabric that allows curvature to exist at all. To glimpse that mystery, we must turn toward the most extreme frontiers of nature, where gravity and quantum physics collide. At ordinary scales, space-time appears smooth, like the surface of a calm sea. But zoom far enough inward to distances near 10 to the power of -35 meters, and that calmness may vanish. There, according to quantum theory, energy fluctuates violently. Space itself is filled with temporary particles and fields that appear and vanish faster than any measurement can capture. In this chaos, geometry may lose its meaning. Distances and durations may blur. The smooth fabric of space-time may break apart into a restless foam. This idea, sometimes called quantum space-time, suggests that the geometry we experience is not fundamental. It is an average, the large-scale appearance of something far more turbulent beneath. Just as a smooth sheet of water is made from countless molecules in motion, space-time itself may be built from countless microscopic events that we cannot yet resolve. The elasticity of the universe, its ability to bend and to ripple, could arise from the collective behavior of these quantum elements. The geometry we see would then be a kind of macroscopic illusion, an emergent order born from chaos. Physicists are now searching for traces of this quantum structure. Some look for small distortions in the timing of light from distant gamma-ray bursts, hoping to catch a hint of space-time's graininess. Others study black holes, whose immense curvature brings quantum and gravitational effects together in one arena. Inside a black hole, gravity grows infinitely strong, but, according to quantum theory, energy cannot compress beyond certain limits. Somewhere between those boundaries must lie the true nature of the fabric. The combination of Einstein's geometry and quantum uncertainty has produced one of the greatest mysteries in science: the black hole information problem. According to relativity, information that crosses the event horizon is lost to the outside world forever. According to quantum mechanics, information can never be destroyed. Both theories are correct within their own domains, yet they contradict each other when applied together. To resolve this paradox, physicists began to suspect that space-time itself might store information in its curvature. The area of a black hole's event horizon, rather than its volume, seems to determine how much information it can contain. This discovery led to a radical new principle, that the information describing a region of space may be encoded on its boundary. This idea, called the holographic principle, suggests that the universe we experience as three-dimensional may actually arise from data imprinted on a two-dimensional surface. If this is true, then geometry itself, the curvature that defines gravity, could emerge from patterns of quantum information. The very fabric of space-time would be woven from entanglement, the mysterious connection that links quantum particles even when separated by vast distances. Imagine that every particle in the universe is part of an immense web of entanglement. The strength of those connections determines how close or far things appear, how space and distance are defined. When the pattern of connections changes, space-time curves. Gravity, in this view, is not a fundamental interaction, but the large-scale manifestation of how information arranges itself. This concept unites Einstein's geometry with quantum mechanics in a profound way. It means that the shape of the universe may be the expression of its information content. Where information is dense, space-time curves inward. Where it is sparse, space expands. Energy, curvature, and information become three faces of the same reality. Even the cosmic expansion of the universe may be part of this story. The acceleration of that expansion, driven by what we call dark energy, could arise from the underlying quantum structure of space-time itself. Vacuum energy, the energy of empty space, exerts a kind of negative pressure that pushes the universe outward. The field equations already contain this possibility in the form of the cosmological constant. Einstein once introduced it to keep the universe static, later discarded it, and then cosmology rediscovered it as the driver of expansion. Everything points to the same underlying theme. Spacetime is not nothingness. It has texture, energy, and information. It can bend, twist, and resonate. It interacts with everything and is changed by everything. It is the dynamic foundation upon which reality unfolds. To say that spacetime is a fabric is therefore not a metaphor, but a statement of physics. It is the closest language we have to describe something that is both geometric and energetic, continuous, and yet perhaps composed of discrete quanta. Every experiment, from the bending of light to the detection of gravitational waves, shows us another side of that living fabric. Still, for all that we have learned, the ultimate question remains unanswered. What gives spacetime its form? Why does geometry exist at all? We can measure its curvature, hear its ripples, and see its shadows, but we do not yet know its essence. The answer, if it exists, must lie at the intersection of relativity and quantum theory, where space and time themselves cease to be separate things. There, gravity may not be a field, but an emergent property of something deeper, perhaps of information itself. In that sense, the universe could be seen as a great conversation between geometry and knowledge, between energy and awareness. The curvature of spacetime would then be the shape that understanding takes when written into the fabric of being. We stand now at the threshold of that revelation. Einstein gave us the geometry, quantum physics gives us the restless energy beneath it. What comes next may show us how the two are one and the same. The next chapter will journey into that quantum realm, where the smooth surface of spacetime breaks into granules, and where the universe reveals the smallest scales of its design. It will ask what happens when the fabric itself becomes grainy, when curvature arises not from smooth bending, but from the flickering chaos of quantum reality. To understand this connection, imagine that spacetime at the smallest scale is a restless ocean. Each point ripples with quantum energy, creating waves that rise and fall faster than any clock can measure. These fluctuations do not occur inside space. They are space. The foam that bubbles beneath the surface is the geometry itself, constantly rearranging. When energy condenses into matter, it adds weight to this ocean, changing the flow of its waves. The result is curvature, the bending we perceive as gravity. This picture unites Einstein's smooth continuum with the quantum world's restlessness. It means that gravity is not an external force, but the collective motion of countless quantum vibrations. The smooth arcs of planets, the pull of stars, and the ripple of gravitational waves are all macroscopic expressions of that microscopic dance. If one could see the universe at the Planck scale, space would not appear empty or flat. It would shimmer like a storm of light, filled with fleeting connections and ruptures, where energy and geometry exchange identities endlessly. Particles would arise as excitations of this foam, local patterns of vibration that persist long enough to be recognized as matter. Even photons, the carriers of light, would be ripples on this same ocean of space-time. This vision redefines the meaning of existence. Objects no longer sit within space. They are expressions of space. Geometry and energy are inseparable, two aspects of the same phenomenon. When space-time curves, it is simply reorganizing the flow of quantum energy. When particles interact, they are altering the geometry itself. Some physicists describe this unity using the language of quantum fields. Each field fills the universe, and their combined fluctuations produce the structure we perceive as space-time. Where fields interact, energy condenses, forming particles. Where energy is high, curvature follows. The vacuum is not a background upon which physics unfolds. It is the engine that drives it. The implications stretch beyond imagination. If geometry and energy are one, then the laws of physics are not arbitrary. They are the inevitable consequences of the fabric's nature. The constants of motion, the speed of light, the strength of gravity, and even the flow of time arise from the properties of this quantum field that underlies everything. Time itself may be a reflection of how quantum information propagates through this network. As fluctuations interact, they exchange information, and the progression of that exchange becomes what we call the passage of time. Each moment is not a slice of an independent dimension, but the state of the network at a particular configuration. The geometry we observe, from the warping near black holes to the expansion of the universe, would then be a large-scale manifestation of how information is distributed in the vacuum. Regions dense with energy correspond to strong curvature, while regions of low energy correspond to flatness. In this sense, the shape of the cosmos is the image of its information content. This idea connects naturally to the holographic principle, which suggests that all information in a volume of space can be encoded on its boundary. If that is true, then space-time itself may arise from the entanglement of quantum states across these boundaries. The stronger the entanglement, the smoother the geometry. The weaker it becomes, the more fragmented and curved space appears. Gravity, in this perspective, is the way the universe maintains coherence in its web of information. Such a universe would not be made of matter and forces, but of information and relationships. The flow of energy, the curvature of space-time, and the progression of time itself would all be expressions of how this information changes. The vacuum would be the substrate of reality, the living network from which everything else emerges. Experiments are beginning to test the edges of these ideas. Observations of black holes, gravitational waves, and cosmic microwave background radiation may soon reveal hints of the quantum structure beneath space-time. Each detection adds another thread to the picture, showing that the boundary between geometry and energy is far thinner than we once believed. If we follow this logic to its conclusion, the distinction between something and nothing vanishes. The vacuum, though invisible, is not the absence of being, but the most fundamental form of it. The universe exists because the vacuum cannot stop fluctuating. Its energy gives rise to geometry, its geometry gives rise to matter, and its matter gives rise to us. In this way, curvature and quantum chaos are two sides of the same coin. The smooth bending of space-time that Einstein described is the collective effect of countless quantum fluctuations, averaged over cosmic scales. Gravity, therefore, is not a fundamental force, but an emergent property, the shape that arises when the vacuum's microscopic activity is viewed from far away. The cosmos we experience is the calm surface of that storm. Beneath every second of time and every meter of distance lies the ceaseless trembling of existence itself. Out of this trembling comes everything we see, from the light of the sun to the spin of galaxies. The quantum grain of space-time is not merely a mathematical curiosity, it is the heartbeat of reality. Each flicker of vacuum energy, each fluctuation of geometry, contributes to the grand illusion of smoothness that we call the universe. But if emptiness is so alive, if nothingness is so full of power, then we must ask what happens when that energy dominates. When the vacuum itself becomes the source of curvature, when energy bends not matter, but nothingness. The next chapter will explore that profound question. It will trace how vacuum energy shapes the expansion of the cosmos, how dark energy drives the galaxies apart, and how the invisible power of nothingness defines the destiny of everything. Einstein showed that space-time bends, but he could not see what happens deep inside that bend. The smooth geometry of relativity may be only an illusion, a surface hiding quantum chaos beneath. If you could zoom in far enough, past every atom and photon, to scales near 10 to the power of -35 meters, the calm fabric of space-time would begin to boil. At that scale, the universe trembles. Energy cannot sit still. Quantum uncertainty demands that every field in space fluctuate, giving rise to brief flashes of virtual particles. They appear, vanish, and reappear endlessly, creating a restless foam. Here, geometry itself loses meaning. Distances flicker. Time becomes uncertain. The smooth fabric breaks into a storm of probability. Physicists believe this is the true foundation of space-time, a sea of quantum energy so dense that every patch of emptiness hums with motion. The Planck length marks the limit of smoothness, beyond which Einstein's equations collapse. If gravity and quantum theory are both correct, the two must meet here. Two great ideas compete to describe what this grainy fabric might be. String theory imagines that all matter and energy are made of vibrating loops, and that space-time itself is born from their harmony. Loop quantum gravity, in contrast, says that space is woven from discrete loops of geometry, tiny, building blocks of area and volume. Both suggest that space-time is not continuous, but quantized, built from the smallest possible units of shape. At these scales, the concept of a force disappears. Curvature becomes a dance of interactions. Space-time is not the stage for energy, it is energy's expression. Gravity becomes not a pull, but a pattern, an emergent rhythm of quantum motion. If this view is correct, then time itself is not fundamental. The flow of moments arises from how quantum states change relative to one another. The illusion of continuity, the feeling of smooth time, emerges from countless tiny transitions, just as a movie appears seamless, though built from separate frames. This quantum view transforms our understanding of gravity. Einstein's smooth geometry may be the shadow of something deeper, a self-organizing network of information, where each connection defines distance and every vibration shapes the form of space-time. The universe we see, solid, smooth, predictable, is the large-scale reflection of that hidden quantum sea. Beneath every curve of space-time lies a storm of creation, a foam of geometry forever flickering at the edge of existence. What if the most powerful form of energy is hidden in emptiness? Quantum theory says that even when space contains nothing, it still seethes with motion. Virtual particles appear and vanish endlessly. The vacuum is alive. This restless activity gives rise to a mysterious pressure, vacuum energy. It is faint, yet it fills all of space. Einstein's equations allow such energy through a term called the cosmological constant, which acts as a uniform push, stretching the universe. In the late 1990s, astronomers discovered that distant supernovae were dimmer than expected. The universe was not slowing down under gravity's pull. It was accelerating. Something unseen was driving it apart. An invisible energy now called dark energy. Dark energy behaves like a negative pressure. As the universe expands, its density remains constant, causing space itself to accelerate outward. It is as if the vacuum is expanding under its own tension. This discovery transformed cosmology. The void between galaxies is not empty, but filled with the very energy that shapes their destiny. The mystery deepens when theory meets observation. Quantum physics predicts that vacuum energy should be immense, 120 orders of magnitude larger than what we see. Something cancels almost all of it, leaving only a faint residue. That residue defines the fate of the cosmos. Perhaps dark energy is not constant but evolves, an echo of the quantum fluctuations of space-time itself. Or perhaps it reflects the geometry of hidden dimensions curled beyond our view. Whatever its origin, it reveals a truth both elegant and unsettling. Even nothingness can bend reality. The universe's expansion, the birth of structure, and the future of all things are written in the silent pressure of the void. Gravity does not only draw things together. In the vast emptiness between stars, it also stretches the universe apart. Black holes are gravity made visible. They are the places where curvature folds in upon itself, where geometry becomes so extreme that even light cannot escape. Imagine a star collapsing under its own weight. As its core contracts, space-time bends ever more sharply until it forms an event horizon, a boundary beyond which all paths curve inward. To an outside observer, time near the horizon slows almost to stillness. Inside, our equations fail completely. This is a singularity, a point where curvature becomes infinite. It is not a place in space, but a failure of geometry itself. Relativity cannot describe what happens there. Only a quantum theory of gravity can. And yet, black holes are not entirely silent. Quantum mechanics predicts that they emit faint radiation, known as Hawking radiation. Over immense timescales, this causes them to evaporate, returning their energy to the universe. This discovery linked gravity, quantum theory, and thermodynamics in one framework. It revealed that even the darkest places obey the laws of information. At the edge of a black hole, the boundary between existence and disappearance becomes thin. Information that falls in seems lost, yet physics demands that it be preserved. This paradox led to a new insight, that the information inside a region of space may be stored on its boundary. This idea, called the holographic principle, suggests that the universe itself might work the same way. At the edge of reality, curvature and information meet. The geometry of the universe may be nothing more than the projection of data encoded on a higher dimensional surface. The black hole, once a cosmic abyss, has become a window into the code that writes reality. On the largest scales, gravity does not simply pull, it defines the shape of the entire universe. Einstein's equations allow three broad possibilities: a closed universe that curves back upon itself like a sphere, an open universe that expands forever like a saddle, or a flat universe balanced perfectly between them. For decades, astronomers sought to measure this cosmic curvature. By mapping the faint afterglow of the Big Bang, the cosmic microwave background, they found that space is astonishingly flat. The total energy of the cosmos, including dark matter and dark energy, seems to balance the geometry almost exactly. This balance is delicate. A fraction of a percent difference would have made the universe collapse or fly apart too quickly for galaxies to form. The near-perfect flatness we observe suggests that the early universe underwent a period of rapid inflation, stretching space-time to cosmic smoothness. Yet, even in its apparent flatness, the universe remains dynamic. Dark energy continues to push it outward, accelerating its expansion. In the distant future, galaxies will drift beyond one another's light, leaving only islands of stars in an endless sea of dark. The curvature of the cosmos, once thought to be a static shape, is revealed as a living geometry. It expands, evolves, and carries the imprint of everything it has ever contained. The question remains, is this curvature fundamental, or does it emerge from something deeper, perhaps from the quantum information that underlies space-time itself? All roads lead to a single possibility. Gravity, the bending of space-time, may not be fundamental. It may emerge from the hidden architecture of quantum information. In this vision, space-time is built not from substance, but from relationships. Every bit of quantum information, every entanglement between particles, defines a link in the fabric. The strength and pattern of these links create geometry itself. When the pattern changes, curvature appears. Gravity becomes the flow of information through this web. The holographic principle suggests that everything we see in 3 dimensions may arise from information written on a 2-dimensional surface. Einstein's equations could then emerge naturally from the way that information interacts. In this sense, gravity is not a force, but a byproduct of the universe trying to stay consistent with its own information. This idea, sometimes called emergent gravity, unites the smooth geometry of relativity with the probabilistic world of quantum theory. It implies that the curvature of space-time, the expansion of the cosmos, and even the passage of time arise from the same source, the quantum network of entanglement that connects all things. If this is true, then the universe is not built from matter, but from meaning. Curvature is the shape that energy and information carve into the foundation of existence. Gravity does not pull, it bends. It is the silent architecture of reality, the shadow of quantum order projected into space-time. And beneath that curvature lies the code, the invisible pattern that writes the universe itself.